Yeah, then it's like for real. It's like, here's Genie. I made the medium version.
Here we go.
Oh, no.
Let's get started. Starting right on time. I had a meeting over in Old Main, so I sort of had to rush to get over here. So, okay. Couple of housekeeping items. So the attendance grades are up to date on Blackboard. I graded homework 1.1. The whole class did very well. As to be expected, that wasn't a hyper challenging assignment. Homework 2.2 is assigned today, but homework 2.1, that was due today. How did homework 2.1 go? I'm hoping that one was pretty simple. So homework 2.2 is assigned today, and this one I made up the problem. So they came out of my noggin. So I'll pull that up here in a second. Real quick, did everybody get the QR code?
Yeah.
QR code, everybody? Okay. All right. Just a heads up. If you go to Blackboard right now, so this is the student preview. So this is what you see now. If you scroll down, there should now be a couple of extra folders. So first off, what I'm going to try and do, and I probably am not going to bat 1,000 on this, but what I'm going to try and do is I'm going to try and use this folder here called Older Assignments. And so if I stick something in that Older Assignments folder, that's a homework that is graded. Okay, so once I finish grading it, I'll stick it in there. And then, so like I say bat 1,000 because, I mean, we might have, you know, if the homework assignments get kind of long, there might be a couple of homework assignments out in here. But the idea is that the one that's always due is the last one here on the main page. And then the other thing is I will have a solution, or there's a solutions folder here. And so I put the original assignment and then I put the solution here as well. So you all are, that way it's all together. So the way that the solutions will work is, so if I assign a homework on Wednesday that's due Friday, the solution will be visible that Monday. So it'll always be one lecture behind. So yeah. All right. Sound good? Okay. All right. And everybody got the code? Okay. So the star of the show today is trig. Or maybe a better way of saying it is, in certain instances, a way of getting around trig. But we'll talk about that as we get to it. But really what we're talking about today specifically are inclined loads and inclined supports, mainly inclined roller supports. Okay. So just to recap from last time, so what have we discussed how to handle so far in this class? We have discussed how to handle concentrated loads. We have discussed how to handle distributed loads. And specifically, the two types of distributed loads we've discussed are a uniformly distributed load and a triangular load, okay, or linearly distributed load. Now, we have discussed pin supports and roller supports. Bless you. We talked about fixed supports. We haven't done anything with them yet. That's Wednesday, okay? So Wednesday, we'll talk about fixed supports, and we'll talk about concentrated moments. But up until now, this is what we've handled in here, even within our first week. So we've already done quite a bit in our class starting out, okay? So what we're going to talk about today is trig. It's basically taking the loads and putting them at an inclination, okay? Now, the big thing about this in an engineering context is that oftentimes we do not, I mean, sometimes we'll express that load at an angle, but oftentimes we don't express them at an angle, we express them at a slope ratio, okay? So what I'm getting at is oftentimes, or before you take this class, you're used to the load, like you're used to this being like physics, right? So you're saying, okay, here's a load, this angle with the horizontal is 35 degrees, so I'll split that up into x and y components, and this will be the cosine of the angle for the x component, the sine of the angle for the y component. And there's nothing wrong with that. That's totally fine. However, oftentimes in engineering context, we'll see loads like this, okay? And basically that's because we often represent slopes as a rise over run ratio. So for example, how many of you have ever had any exposure or experience with carpentry, and when you're talking about roofs, it's a 4-on-12 pitch or a 6-on-12 pitch? They don't say that the roof is a 57.42 degree angle or whatnot. They'll say 4-on-12, 6-on-12, right? And so dealing with those numbers directly often will save you button crunching on the calculator, okay? So for example, if I have this triangle where the bottom leg is H, the top leg, or the horizontal leg is H, the vertical leg is B, and then the hypotenuse, we'll call that R, okay? So let's say I'm talking about this angle right here. Well, what is the sine of that angle? Well, it's opposite over hypotenuse. It's V over R, right? What is the cosine of that angle? It's H over R, right? So instead of saying, well, I have a slope ratio, I need to take an inverse tangent to get an angle, and then take the sine and cosine of that angle to get those components, just use SOHCAHTOA, right? Just say H over R or V over R. And we're going to use that quite a bit in here because it's faster, okay? Now make sure that when you're doing this, and it's actually, I think there's probably more room for error here, in my opinion. That if you're, if you still prefer using the angle, that's fine. Just make sure the angle is referenced from the horizontal if you're going to just plug and chug these expressions. Because if you say the horizontal component is related to the cosine and the vertical component is related to the sine, that is assuming that the angle is referenced from the horizontal axis. So if the angle is referenced from the vertical, you got to flip those trig functions or do 90 minus the angle. Okay? Does that make sense to everybody? Everybody okay with that? Okay, I'm hoping that's sort of straightforward at this point. Now, let's practice that. Let's do an example, okay? So I'm going to give you this example, and we're going to go through this one together. So it's a lot like what we did last time, only instead of having a point load that's just vertical, I've got one at a bias, one at an angle. So let's see if we can knock this one out. Okay. Oh, wait. That's the wrong one. I need to do this one. Example 3. We're going to do example 4 here in a bit. Okay. So we're going to compute the support reactions of this beam. And notice how it's a simply supported beam, just a hinge support at A, roller support at B. And we've got, our familiar distributed load right here. But now we've got this angular load that we've got to deal with. Okay. So let's handle this problem like we've been handling reaction problems so far, okay? So let's start off with our unknowns. How many unknowns do we have at A? 2. Okay. Now, what I'm going to do is I'm going to draw the vertical one. Oops. Going to draw this one like that, and what I'm going to do here is draw this one like that. Okay. Now, I'm going to peer into the future a little bit, and I'm going to tell you that assumption for AX, the direction, is wrong. Okay, that is not the correct assumption in terms of it acting to the right. I'm sort of doing that on purpose because we haven't done that yet in class yet, and I just want us to get familiar with what happens when our assumed direction is incorrect. Okay, because it's not really that big of a deal. But I'm afraid if you're doing the math on a homework or an exam and you get a negative answer, I don't want you to panic. Okay, so we do kind of need to get used to that. Okay. Now for B, we'll assume that acts upward. Okay. So far so good? Okay. All right. So before we deal with this inclined load, let's deal with the stuff we're familiar with. Somebody tell me what we ought to do with this right here. What do we do here?
Make it a point load.
Make it a point load. What is the magnitude of that point load?
14.
14 kips. So we'll put that. Okay. Oh. Let's do it like that. What is that dimension right here?
5 feet.
5 feet. Okay, just halfway over. Okay, that part's pretty easy. Okay. Okay, so, all right, I want to go through an exercise with this triangle to sort of make the point that I was talking about. Okay, so let's do this. Let's do this over here. Okay. So there are two ways of dealing with this triangle. Okay? So we're given 3 and 4. Okay? I'm going to do this the hard way and then do this the easy way. Okay? Let's do this the hard way. Okay? Let's say that you like using trig. So how do I compute that angle?
Inverse tangent of 4/3.
What is that? Has everybody brought their calculator FX 115 ES plus or similar scientific calculator? It should just be like at the ready.
degrees.
53.13 degrees. And then if I wanted to take the cosine and sine of that angle, what's the cosine?
0.6.
0.6. What about the sine?
0.8.
0.8. That's the hard way, in my opinion. Here's the easy way. If that's 3 and 4, what's the hypotenuse? 5. So the cosine of that angle is, wait, hold on. Yeah, adjacent over hypotenuse, sorry, my coffee wore off, is opposite over hypotenuse. Isn't that so much easier? So what I'm getting at is we can just sort of avoid the usage of the trig altogether, okay, by just using the slope ratio. I mean, we're doing the trig, but we're not using the trig function. So, and notice how you needed a calculator this way. You didn't need a calculator this way. Just saying. Okay. So, again, I'm not a micromanager. If you prefer this method, that's fine. You do whatever makes sense. I'm just, this is a little bit faster. Okay. So this 20 kip load, okay, so let's talk about this. Okay, so I'm going to split this up into X and Y components. Okay. So what I want to do is say, okay, I want to idealize this as a vertical load and a horizontal load. So let's deal with the vertical load first. Okay, what is the magnitude of that vertical load? I'm going to take 20 kips times what? 4/5, which is 16 kips, right? Okay, and this one right here, I'm going to take 20 kips times 3/5, Okay? All right, so let's make sure we understand how we get these fractions. First off, the denominator for both of these fractions is the hypotenuse, okay? And as for what's the numerator, just say the horizontal goes with the 3, the vertical goes with the 4. It's that simple. Okay. Now, what about the directions? The vertical load, is it up or down?
Down.
Down. Okay. The horizontal, is it left or right?
Right.
Right.
Right. Okay. So just follow the direction of the loads that goes. Now, I made a little bit more to do this than just doing it, but when we get into trusses, being able to identify those directions is pretty important. Okay. All right. Everybody good so far? We're good? Okay. So tell me what to do.
Some forces in horizontal direction.
Some forces in the horizontal direction. Okay, let's go ahead and do that first. First off, let's just not do any math. Is AX going to be 0?
No.
No. Okay, so let's handle this. Okay, so let's do that. Let's do that. Okay, so we'll do all the forces to the left, all the forces to the right. And let's handle this like we've been doing this whole time. Okay, so do we consider AX?
Yes.
Which side of the table, left or right?
Left.
Well, hold on. Which way do I have it drawn?
Well, it's going to the right.
I know. So we're going to stick with that for right now. I know what you're thinking. You're thinking that's wrong, right? I know that. But right now, we're going to assume we don't know that. Okay? I have it drawn to the right. I'm putting it to the right. Okay? That's the way the arrow's going. I'm just going to go with that. Okay? I have assumed at the beginning of this problem that it's going to the right. Let's just hold to that. Okay? Now, what I'm getting at on this problem, I think it's pretty easy to see that assumption's wrong. But what if you've got vertical reactions and you have 8 or 9 loads? It's not that simple. Okay? So let's just adhere to the assumption that we made at the beginning. Okay? Do I need to consider AY? Do I need to consider the 14 kips? What about the 16 kips? What about the 12 kips? Which direction? To the right. Okay. What about BY? Is that it? Okay. So what's happening is I've got a bunch of stuff over here. What do I have over here? Nothing, right? Nothing. So this is 0. Is AX plus 12. So if 0 equals x plus 12, what's x?
Negative 12.
Negative 12. So I got a negative answer. Okay? So what I'm saying here is that therefore AX is minus 12 kips. Okay? Now what does that mean? Okay? I assumed that AX was acting to the right. I got a negative answer. What does that mean? It's acting to the left. Okay? Because here's the thing, okay? Let's look at this part, just this part right here. Let's look at the part in red. Okay. I assumed that AX was acting to the right. I got a negative answer. What if you assumed that AX was acting to the left? What would you get right here in red? AX equals positive 12. What I am saying is that at the end of the day, this part doesn't really matter. What matters is that. At the end of the day, whether you assumed right or I assumed left or vice versa, doesn't matter. What matters at the end of the day is that we both get this. Okay? This is the truth. Okay? The truth is that AX is 12 kips to the left. That's why when I ask for your final answer, I don't care if the answer is positive or negative. It doesn't matter. This is what matters. Okay? Does that make sense? Now, I'll give you one reason why I'm harping about this, and the reason I'm harping about this is because of software, okay? Software, by default, makes standardized assumptions for reaction directions. In other words, so let's say vertical reactions. Anytime you do a software analysis, like when we use masthead, it'll assume all the reactions are upward every time. So if you get a positive reaction, it is acting upward. If you get a negative reaction, it's acting downward. But you need to know what the assumptions are at the very beginning in order to make sense of what it's spitting out. Okay? Make sense? All right. I'm not done. Tell me what I need to do.
Sum the moments.
Sum the moments where?
A.
Okay, we'll do A. Could we sum them at B?
You'd have a lot more unknowns if you did that, though, right?
Why? Let's talk about that. Why?
Because there's less things passing through B.
Okay, my three unknowns. Does AX pass through B?
I guess, yeah, it does.
It does. It doesn't generate moments. So we could sum moments at B and it would isolate AY. Let's do that. Just to be different. Let's see what happens. I'm being different today. Okay. All right. So, let's see what happens. Do I need to consider BY? Do I need to consider, so let's start here and work my way over. Do I need to consider the 16 kips? The 16 kips right here. Does it generate moment at B? Okay, what's my moment arm? 6. And so if I'm at B going like that, 16 times 6, that's over here. Okay. What about the 12 kips? Do I need to consider the 12 kips? No. And I do want to make like just an artistic statement right here. So some of you might say, well, wait a minute. The load is on the top of the beam and the roller's on the bottom of the beam. So isn't there like a little bit of a distance there? Yes, if you consider the validity of my artwork here. Usually when I draw these problems, and what most textbooks do, is they will draw the beam with some depth just so that like you know it's a beam and not just a random line on the page. But for the purposes of a structural analysis, at least until we say otherwise in here, you can assume that beams have no depth. In other words, it's really just a line. Okay? So yes, this load, we're saying it passes through B, just like the roller does. So we're not going to consider that horizontal load. All right, what about the 14 kips? Does it generate moment at B? Yep, and so that moment arm is what, 19 feet, right? Because it's 24 minus 5. So 14 times 19. All right, and then that's going to be counteracted by AY times 24. Okay? I mean, is that accurate? So AY times 24 equals, okay, 16 times 6, that's 96. What's 14 times 19? Because I didn't do it this way, I did it differently. Is that
266.
266? All right, so was that 362? Did I get that right?
Yep.
Well, I'll be. Maybe my coffee's kicking in. Okay, so 362 over 24. What do we get here?
15.08.
Is that positive? Did we get a positive answer for AY?
Yes.
Yeah, we did. Again, I don't care about the positive number, though. What I care about is the fact that we make the connection that that positive value means that our initial assumption for direction was correct. Now, what's left?
Some in the F direction.
Some forces in the Y direction.
Oh, why?
Yeah. So, but yes, you're right. So we have AY. We have BY. Then down, what do we have? We have 14 kips, 16 kips. Do we have the 12? Do we have to worry about that? No. Okay. Okay, I think I can do this one in my head because, I mean, 30 goes into 15 twice. It's going to be about 15. Was that 1492?
Yep.
Okay. So to summarize, just to put myself a little summary here. Okay. All right. So let's take a step back. Did this make sense? This isn't that difficult, is it? Should be pretty straightforward. Anybody have any questions on this? Now I'm going to take this and I'm going to make it a little bit more complicated, or this idea of inclination. All right. But has everybody got all this? Do I need to keep this up for a minute? I'm going to take that as a I'm good to go. Okay. All right. Okay, now my second example and my last topic for today's lecture that I want to discuss is the idea of an inclined roller. Okay. Now I want to preface this by asking you a question from math. Okay, particularly I guess algebra. So I have a line, y equals mx plus b. I plot the line. Okay, and I want to know what is the slope of the line perpendicular to that. So if I have y equals mx plus b and I have the slope, how do I find the slope of the perpendicular line? How do I do that? Anybody remember how to do that for math? It's been a while, hasn't it? Does this ring a bell that if I have a line and I want to find the slope perpendicular, I take the slope and I reciprocate it? Right? So if I have a line and its slope is 2/3, that the slope of the line perpendicular to that is 3/2, or I guess negative 3/2 because you got to flip the sign too. Do y'all remember that? Has it been a while? I mean, I'm not. You've never seen that before. Everybody's seen this before, right? Okay. All right. So what that means is that why am I bringing this up? Let's ask it this way. Why am I bringing this up? Well, I'm bringing this up because what if your support is inclined? What if you have an inclined roller? Well, if that's the case, you have to flip the slope ratios too. Okay. Now, I have an example here on the board that you can reference, but I kind of want to walk you through one that's maybe, I don't know, a tad more extreme, but you'll understand why I'm doing it. Okay? So, let's do this. Let's assume that I have a roller, okay? And let's say that the ground has a very, very light slope. Let's call it a 1 to 12, okay? I'm just offhand curious. Does anybody know why I would use a slope from 1 to 12? Does anybody know where that slope arises in the real world? You look like you're about to say something.
Isn't that typical slope that the road is at? Like,
Not thinking about the road.
okay.
Not thinking about the roof. I'm thinking about the ramp right out here outside the building. Handicap accessible ramp. Typically, maximum allowable slope is a 1 to 12. Okay, so it's a value that we would see in the real world. Okay, because think about the stairs right here. There's a very short amount of stairs. What is it, like 6 or 7 stairs to get from the sidewalk to the entrance to the engineering building? But the ramp goes on, right? Because for that short elevation difference, you got to go out the factor of 12 in order to meet that requirement. Okay, does that make sense? All right, so now I want you to think about the reaction component, okay? So what would the reaction look like? So the reaction would be perpendicular to that, and it would be like this, okay? Now, let's do some math here, okay? So 12 squared plus 1 squared is 145, so this is square root of 145, right? Is that right? So what's 12 over 145?
The cosine of that interior angle.
I know. I'm asking, like, what is 12 over square root of 145? It's going to be a big number.
Shouldn't it be close to 1?
It's going to be big, yeah. Like, that's what I mean when I say big. I mean close to 1.
Yeah, 0.9965.
0.9965, okay? So what I was saying is that the road is or the ground is barely sloped. So most of the reaction is vertical. So I'm going to stick the vertical component of this reaction is going to be the 0.9965 R, right? The smaller component is going to be the horizontal, and it's going to be very tiny, right? But here's my point. That's backwards from what we did here. That's backwards what we did here, right? Because what we did here is we said, when we split this up into horizontal and vertical, we'll stick the 3 over 5 with the horizontal and the 4 over 5 with the vertical. Now we're doing the inverse, okay? Because now we're taking the 12 value and sticking it with the vertical, and whatever the 1 value is and sticking it with the horizontal. They're flipped, right? Why are we putting the bigger number with the vertical when the bigger number here is with the horizontal? It's because it's perpendicular, right? That's why. We're flipping the ratio, okay? Does that make sense? All right, does anybody have any questions on that? I think the best way of working through it is to do an example. So let's do an example. Let's do one. So I have a triangular load on a beam that the roller is inclined by an angle of 20 degrees. Okay? So we're going to see if we can compute the 3 reactions here. One of the things, though, about inclined rollers is that it sort of feels like there's 4 unknowns to this problem, not 3, okay? Because there's going to be, let's talk about the unknowns. So I'm going to have a horizontal reaction at A, a vertical reaction at A, and then I'm going to have a reaction at B that I'm going to split up into horizontal and vertical components. The difference between them is that AX and AY are completely independent of one another. They aren't related, whereas BX and BY are related, okay, because they must respect the slope ratio, okay, and that's why there's only 3 independent unknowns, okay. All right, so let's see what we can see here. Okay, all right. First off, let's deal with the stuff that we're comfortable with. Let's deal with the quote-unquote the easy stuff first. Let's deal with this triangular load. If I wanted to idealize this as a single point load, what would the magnitude of that point load be?
144.
What's that?
144.
How'd you get that?
By multiplying 4 and 26.
And what's next? The area of the triangle BHF. over 2. We have to cut that in half. That's a very easy thing to forget when doing these things. So it's not 4 times 36. It's 4 times 36, but half of that. Okay, because it's a triangle. Okay. So what is 4 times 36 over 2? It's 36 times 2, which is 72. Did I get that right? When I make solutions for exams, that's still a mistake that I often do. Whoop, forgot that, so that's okay. All right. From A, where do I place this 72 kip resultant?
12 feet.
There we go. Okay. All right. Now, let's talk about A. How many unknown reactions are there? 2. Okay. Now, I am going to draw those up and to the right. Okay. The horizontal one, I'm going to put that one to the right. Okay, I'm going to put that one to the right. All right, now I am going to violate my rule a little bit because I gave you an angle. I didn't give you a slope ratio, so we're going to go ahead and break out the trig. So let's do that. Okay, so okay. So this is a 20-degree angle. Okay. So somebody tell me what is the cosine of 20 degrees and what is the sine of 20 degrees. Here, I'm going to move this over a little bit. I'm going to move that on over just a little bit. We'll say to 3 decimal places. What is cosine of 20 degrees?
0.940.
Cool. Yeah, that's right. Do I have a second on that? That's right. And then the sine of 20 degrees?
0.342.
And just a quick little math review. If we take the cosine squared plus the sine squared, I kind of believe that's a trig identity that says that's 1, right? Cosine squared plus sine squared is 1. Okay. All right. So, okay, with that knowledge in mind, let's draw our reaction at B. Now, what direction shall we assume for the reaction at B? And I'm not talking about the components, I'm talking about the reaction at B. So what are the directions that we have available to us? It's either kind of up like that or kind of down like that. It's not up and down or left and right. This is an inclined roller. So the reaction is going to be in this direction. It's either going to kind of go up like this or down. So you want 1 or 2? 1. Okay. So the reaction, the actual reaction, is going to look like this. And those are the 3 unknowns. AX, AY, and RB at this sort of inclination. Okay? Now, what I want to do, and as a general rule in this course, whenever I see things at an angle, I find it to be a lot easier if I take them and resolve them into their X and Y components. Okay? Now my question for you, if this is RB, for this vertical component, if this is RB, what is that vertical component?
RBY.
Well, RBY, but how much, but my question is, don't we already know that this vertical component is RB times some ratio? What's the ratio? 0.94. That's what I'm saying. I'm saying that this vertical component is that. We already know that. Just as this horizontal component is what I am saying is that this roller is at an inclination. It only has one unknown. These x and y components are percentages of that. And how do we determine those percentages? With trig. Okay? They have to be related. This is just taking a vector and breaking it up into its ij components. That's really what we're doing. Okay? Does that make sense? Okay, so let's see what happens here. Now, my suggestion is going to be to sum moments. Okay? I'm going to sum moments. In this case, I'm going to sum moments today. Okay. So now let's take this one step at a time. Okay, do I need to consider AX or AY? No. Do I need to consider the 72 kips times a moment arm of? There we go. Okay. I don't think I need all that. Okay. Do I need to consider, okay, now let's look at B. Do I need to consider this horizontal component at B? No, because, I mean, I drew it lower, but really where it's acting, like if I wanted to be technically precise, really where it's acting is right there. You know what I mean? I just drew it down because that's where the angle was. But it's going right through A, so it's not generating any moment at A. But the 0.940 RB, now that one is. And what's that moment arm?
36.
Okay. And that's it. So 72 times 12, that's 864, is 0.940 RB, is 36 feet, or times 36 feet. So to solve for RB, I'm going to divide 864 by 36, but I'm also going to divide it by 0.94. Okay? So what do I get for RB?
25.5.
Okay. 25.53. Okay, now I got a positive value. Okay? That means my assumption was correct. Okay? Now, here's the question though. What was my assumption? Was it this? No. Okay? RB is not the vertical component. RB is the angular component. So instead, what I'm going to do is do it like that, to say that really RB is going like this. That is the assumed direction. Sound good? Okay, now tell me what to do. What do I do? Well, how many unknowns do I have left? And what are my two unknowns, by the way? AX and AY. Do I know what all three of these values are? Yes, because they're all related to the RB. Now that I have the RB, I know all of this. The AX and AY are the true independent unknowns. So it really doesn't matter what order you do this in. So you want to do X first? Let's do X. So, I mean, let's just use some common sense here on this one. So how many horizontal loads do we have? We have two, right? We have AX going to the right, 0.342 RB going to the left, right? So that tells me that my assumption for AX is correct, and I can calculate AX right now by just saying AX is that. And so, what do we get for that? You go away. So what do we get for that?
You're at 8.73.
All right, do I have a second? And that's going to go like that. And what's our remaining equation of equilibrium? That's just sum of the forces in the y direction. Okay. So I'm going to have AY going up, 72 going down. And what else am I going to have going up? I'm going to have 0.940 RB going up, right? But again, we know what RB is. So therefore, we can just solve for AY directly. By taking 72 minus this, and what do we get? I'm going to scroll that up a little bit so it's a little easier for me to write. 72 minus that times that.
48.
48. So what's my answer? That. And RB and then add an angle. And I'm going to pull up my homework assignment for you here in a second. Okay. Anybody have any questions? It's not too bad, right? Again, we're starting slow, and we're just sort of ratcheting it up just a little bit each time. Okay. All right. So let me pull up the homework assignment real quick just to show you. Does anybody need me to leave this up for a second? Okay. So make sure and pull up the assignment and not the solution. Okay. So here's the assignment. So I made these problems up myself. So we've got both problems have an inclined roller. One's an angle, one's a slope ratio. This one has an incline load on it as well. So what?
Second problem.
Too much work.
Interesting.
If I'm being honest, I think the first one's harder than the second one.
Yeah,
So.
you might be right.
Too much work.
All right. Sound good? I'm going to pull up the code one more time, everybody, and I will see you all tomorrow with, if you're in lab, with closed-toed shoes.
I think close to the